Welcome to day 3 of at-home digital learning, courtesy of the coronavirus. I hope that previous YouTube video was a good reminder of some of the differences between a linear function, a quadratic function, and an exponential function. So here are the 3 types of functions. So your linear function is written in this form, y equals mx plus b, where m is your slope and b is your y-intercept. Quadratic function, we have our a, b, and c. Remember that we are able to find our vertex by doing negative b over 2a, and then we plug that back in order to find the y value of our vertex. We also have the exponential function, which is something you covered in secondary 1, but you probably haven't thought of in a very long time. So this a is still your multiplier. The bigger that a is, the faster it's going to increase. And the b is what is considered your base. So your base has to be greater than 0 in order for this exponential function to exist. So let me give you an example of graphing an exponential functions just really quickly, because I know we probably haven't thought about it in a very long time. So let's pick some values for b, and let's find out what our y values are. So if I let b be 2, okay, and this shouldn't be b, it should be x. So let's assume that we're doing this for b equal to 2. If I plug in 0, that would be the equivalent of saying 2 to the 0 power. Anything to the 0 power is 1. So that's going to give me this point 0, 1. And this point is the exact same point no matter if b is 2 or if b is 1000. Then we would choose x equals to positive 1, which would be 2 to the first power, which is 2. So we would go over 1, up 2, 1, 2. And there's my point 1, 2. We could keep on going. We could do when x equals 2, so 2 squared would give me 4, and that would be this point way up here, would be 2, 4. You can also go in the negative direction over here. So what if x equals negative 1? This would be b to the negative first power. So in this case, it would be b to the negative first power. And if you think way back to Unit 3, we learned that a negative exponent just means put that whole thing in the denominator. So b to the negative first power is actually equivalent to 1 over 2 to the first power, which is 1 over 2, which would be 1/2. So this would be this point right here would be negative 1, 1/2. And you could do this for negative 2 as well. So 2 to the negative second power means that we take 2 squared and put it in the bottom. Well, what's 2 squared? 1/4. So we actually decrease in height as we move to the left. One important thing to notice about exponential functions is this line looks like it touches the x-axis, but it will never touch the x-axis. So down here below, it gives you a chance to kind of recap some of the things that you remember about exponential functions from secondary 1. You may not remember it from Sec 1, but maybe think about some of the things that stood out to you in that video or in the explanation that I just gave. Remember that exponential functions are just any value raised to an exponent. And from that video, you can recall that exponential functions increase really, really fast. So let's get real for a minute. If exponential functions, think back to the example video, and let's talk the Rona. Okay, if you had to place the coronavirus, the scare of not the scare, the reality of it spreading so quickly. If I were to graph the spread, think about the graphs that you've seen. They've all looked like this, right? Where, for example, if you go on to the New York Times website, they have this exact graph, and it says right here, it says January 2020 in the US, and there's no cases. And then we have like January 14th, and those were the first cases to enter the US. And then now this is March, and oh man, I haven't even thought about it recently, but there's something like 3,000 cases already in the US. So it is increasing at a crazy rapid pace, meaning that the coronavirus spread would be an example of an exponential function, exponential growth. So some of the major differences between exponential functions and quadratic functions. So exponential functions are always increasing. Apologies, increasing. Here we go. Increasing. So exponential function starts low, goes high. A quadratic function, though, is symmetrical and has 1/2 of it will be increasing, while the other half is decreasing. So there's an obvious turning point when you're thinking about a quadratic function like this versus an exponential function. Quadratic functions are also symmetrical. There's some symmetry here, no symmetry here. Quadratic functions, while they increase rapidly, they do not increase as fast as exponential functions. And you will hear me say that so many times in this video because that is one of the huge takeaways that we need you to recall is exponential functions will always be the fastest increasing functions. Linear is always lowest, followed by quadratic, followed by exponential. So let's see some of these in action. So let's compare some linear, quadratic, and exponential functions. So before we can compare them, you can try and compare them by just looking at the equation, but you're going to get the best comparisons looking at graphs. So let's practice making a table and graphing each of these functions. So we have our t-chart down here at the bottom, so we're going to do x values and y values for each of them. Now to make things less confusing, I'm only going to do one graph at a time. I'm not going to go across the board like I just did there. So this first one, this would be an example of a linear function. And I know that because the exponent with the variable x is just 1. So we could plug in, let's do -2, -1, 0, 1, and 2. That gives me a pretty good center point of my graph. So those are great 5 points to do. So to find the y value when x equals -2, I'm going to replace x with -2. So I get 2 times -2 plus 1. I'm going to type that in my calculator, and I get 2 times -2 is -4. -4 plus 1 is 3. No, that's not right. It's -3. So I go over here to my graph, and I'm going to go over 2, 1, 2, down 3, 1, 2, 3. And let's do the same thing with -1. So 2 times -1 plus 1 is going to give me -2 plus 1, which is -1. So now I'm going to go over 1, down 1. Okay, 0, 2 times 0 plus 1 gives me a final answer of 1. Which makes sense because if we recall, that's my y-intercept. Now I'm going to my positive numbers. 2 times 1 plus 1 is 2 plus 1, which is 3. 1, 1, 2, 3. And do the 2 for good measure. 2 for 2 plus 1 is going to give me 5. So over 2, up 5. 1, 2, 3, 4, 5. Awesome. So there's my first graph. Now we're going to do the same thing with the exponential function. You are absolutely going to need a calculator for this one. If you don't have a calculator, what you can do is use the Google search engine, and you can just type it in like this, and you would go 2, and then you hold down Shift 6 to get the caret key that looks like this, and then you would put in whatever value we're plugging in, and then you add 1 to it. So if I choose the same values as I did before, let's do -2, -1, 0, 1, and 2. So I'm going to get 2 to the negative second power plus 1. So if we do that, I actually end up with 1/4 plus 1, which is going to give me 1 1/4. I'm going to go over here to my graph. That gives me -2, 1, 2, 1 1/4. Okay. Now let's do -1. So 2 to the negative first plus 1 is going to give me 1/2 plus 1, which is going to give me 1 1/2. So you'll notice the differences in exponential graphs on the negative side are very, very small. Then we'll do 2 to the 0 power plus 1, which is 1 plus 1, which would give me 2. So 0, 2 is my y-intercept. Then we're going to have 2 to the first plus 1, which is going to give me 3. Over 1 up 3, 1, 2, 3. And then 2 to the second power plus 1 is going to give me 5. So over 2, 1, 2, up 5, 1, 2, 3, 4, 5. Now you want to remember that there's an asymptote here, which means we're never actually going to touch this line. Okay, so when we draw this graph, it's just going to kind of go off to the side. Okay, finally we have our quadratic function. So again, let's use our same x values, -2, -1, 0, 1, and 2. And let's plug things in. We've got -2 squared. Remember, if you are using a calculator, you must use your parentheses. Plus 2 times -2 plus 1. And you get 1. So -2, 1, 2, up 1. Yay! -1 is going to give me -1 squared plus 2 times -1 plus 1, and that actually gives me 0. So there's my y-intercept. Y-intercept is whenever that y value equals 0. False. X-intercept is whenever the y value gives you 0. Then we do the same thing for 0. So 0 squared plus 2 times 0 plus 1. And remember that these are symmetrical. So at this point, you have your 3 dots that you need. But let's keep plugging things in. So we get 1 squared plus 2 times 1 plus 1. And we end up with 1 plus 2 is 3. 3 plus 1 is 4. And then this one, 2 squared plus 2 times 2 plus 1 is going to end up with 9. 1, 2, 3. Nope, sorry. I miscounted. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there's my one side. If you're hesitant, you could have tested numbers on the other side as well. Okay, so some of the things to notice are your rates of increase. So all of these have a scale of 2, but because they are in different spots with different exponents, that's what gives you your variations in your graphs. So in the instructions, it says to list key features like domain, range, intercepts, rate of change, intervals, where the function is increasing or decreasing. So now let's do that. We have got lots of room down below, so we're going to do that here. So we've got domain, range, let's see, what else does it ask for? X-intercepts, Y-intercepts, rate of change, and then increasing and decreasing. Okay, so if we were to split these up, right, so I'm not going to write all of that, basically creating myself a nice neat table here. Keep my work nice and organized. Always a good idea. Okay, and let's talk domain. All of these have a domain of all real numbers. Because of these arrows here, there's nowhere that it can't go. So all real numbers, all real numbers, all real numbers. Awesome. But the range, on the other hand, are very different. For a linear function, your range is also going to keep going to all real numbers. There's nowhere it can't go. But for exponential functions, it's never going to go below this line. It'll never actually even touch that line. So the lowest point it'll ever be is when y equals 1. Then there is no limit, so it goes to infinity. Notice I'm using the parentheses there because it's never actually going to touch that line. Then I have my quadratic, which does touch this line. So that one is going to get a bracket instead of a parentheses. Your x-intercepts here, oh, this one crosses at a fraction. So how could we find the x-intercepts if it's not obvious? Remember that we set the equation equal to 0 and solve. So that would be 0 equals 2x plus 1. And now let's solve for x. So subtract 1, negative 1 equals 2x, divide by 2. So your x-intercept is at negative 1/2 and 0. Over here, there is none. It will never touch. And then here, there's only 1 point. And we actually already found it over here. It's negative 1, 0. Your y-intercepts are positive 1, positive 2, and here also positive 1. Rate of change we're going to talk about a little bit later, but your rate of change is kind of tricky. So your rate of change, if you recall from who knows when, it's always your rise over your run. So it's your change of y values over your change of x values. So let's just pick an interval and let's see what the change is. So if I pick these 2 points right here, sorry, I'm going to zoom in. If I pick these 2 points right here, I've got a rise of 2 and a run of 1. So my rate of change is 2 over 1. Now, if I do this here, notice that there is a much wider variation. If I picked these 2 points, it would only be a rise of 1/4 over 1. But if I pick these 2 points, it would be a rise of 2 over 1. So it's very inconsistent. And later when we talk about rate of change specifically, if I ask you for a rate of change on anything other than a linear function, I have to give you designated points to use. I can't just say, what's the rate of change? I have to tell you what's the rate of change from 1 to 2, and then you would be able to locate the correct rise over run. Same thing with quadratics, like if I were to use these 2 points, it's 1 over 1. But if I were to use these 2 points, it would be 1, 2, 3, 4, 5 over 1. So again, if it's anything other than a linear function, you must have an interval before you can answer that question. Oops, must have an interval. Okay, increasing and decreasing. So this graph is constantly going up. So this one is increasing from negative infinity to positive infinity. Okay, this one is also constantly increasing. So you've got negative infinity to positive infinity. Quadratics are the only ones that are going to have some parts increasing and some parts decreasing. So it's decreasing from negative infinity until we reach the vertex at -1. So that's my decrease. And then it's increasing from, -1 to positive infinity. Okay, I'm going to go ahead and stop there and let you kind of digest because that was a lot of information. So take a break, go get a drink of water, stretch your legs, and I'll see you back in a moment.